So questions 5 and 6 from the mat then, just the final part of this series. So we've got the Fibonacci numbers here. So f3 is just this plus this, f4 is going to be 2 plus 1, and so on. We know the Fibonacci numbers. How many times we need to calculate stuff to work out f of n? Well, f of 3 just took one addition because we already had these two to go. F of 4 takes two additions. First you do an addition to find f3, then another one to find f4. F5, sorry, takes three additions. One to find f3, one to find f4, and then one to put those together to find f5. So the answer is going to be n minus 2, right? Because you have already got these two ready to go. So you just need to do one addition for every one after that. Now we've got a length of sequences 0, 1s, where we're not allowed to have consecutive ones. Of course, the idea here is that we're going to try and connect these things to these Fibonacci numbers here in some way. So what are S1 and S2? The number of ways to write a sequence of length 1. Well, that's just 2, because you can either do a 0 or a 1. And S2 is 3, because the only one you can't do, you can do 0, 0, you can do 0, 1, 1, 0. You can't do 1, 1. So that's going to be 3 of them. Now, let's now formalize this. Can we find a logical way to connect the Sn numbers to the Fn numbers and conclude this thing here? So the way that I did this was I thought about S3, which is 5. They're written down here. Now, the way to construct this is you just take all of the ones that you've got in S2 and add a 0 on the end. So just add a 0, to get here, add a 0. And now there's one extra thing you can do, which is the ones that end in a 0, you can also add a 1 to. So this becomes this, and this becomes this. You can't add a 1 to this one. That's the only thing that you can't do. So we can take all the elements of S2 and add a 0, and we can also take all the elements of S2 that end in a 0 and add a 1. That's kind of how I'm constructing the next one. But of course, when you add a 0 to all of the ones in the previous thing, that's just you make as many things as was in the previous thing. They just all have a 0 on the end. And now what about the other bit where you add 1s onto the ones that end in 0s? Well, the ones that end in 0s, using the logic that I just said twice, the ones that end in 0s are the number of things in their previous set, right? Because this just had a 0 put on the end of it to make this, and this had a 0 on the put in this. So the number of ones that end in 0 in this set are the number of those is the same as the number of things in the previous set. So those ones that I'm going to add a 1 to are just the number of things in the set before the one that you're thinking about. So therefore, to list all the things in Sn, it's just going to be the number of things in Sn minus 1, because you just add a 0 to all of those. And then you take the number of things in the previous set to that, and you add a 1 to those, because firstly, they'll have had a 0 added onto them to make things in Sn minus 1, and then you add a 1 onto it to make the ones in your Sn. So you end up adding the size of the two previous things together. That was probably a convoluted way of doing it, but that was the way that I at least made the connection. Hence, show Sn is equal to Fn plus 2. Well, now that we've got this logical connection, we can just see that the S's are 2 ahead of the F's, because we don't have this 1, 1 business going on. We go straight into 2, 3, 5. So therefore, we definitely have this connected as well. Okay, for n greater or equal to 2, by considering stuff that show this thing here. So let's take S values that are, well, firstly, of course, I don't really want to prove this. I want to prove S equal to S squared plus S squared. Like, I want to use this connection between the S's and the F's to show this. So I'll show this for the S's. Now, like we said, the S's are always 2 behind the F's. So therefore, this thing here is going to be S squared of n minus 2. And this thing here is going to be S squared of n minus 3. And this thing here is going to be S squared of 2n minus 3, because we're always 2 inputs behind the previous one. So what I'm actually trying to show is this thing here, which makes sense because I'm supposed to consider valence sequences of 2n minus 3. So let's do that now. Let's consider sequences of 2n minus 3, and specifically they're poking us in the direction of considering the nth minus 1 position. So if we say this is the n minus 1th term, that means there are n minus 2 terms to the left of it, and that means if they need to add up to have overall 2n minus 3 terms, you've got n minus 1 terms here, I think, because it's going to be n minus 2 plus this one here. So we still need another n minus 2. I think if we do this plus this, we get 2n minus 4, plus the middle one makes 2n minus 3. So this is correct here. Now, why is this relevant? Well, if you have a 0 in the middle, like I've got done here, I can have anything I want either side, because 1, 0, 0 is allowed, sorry, 1, 0, 1 is allowed, or 0, 1, or 0, 0, 1 is. I can have anything either side, which means there's no restrictions on these two sequences here. So I just need any two valid sequences that are allowed to exist under this rule. So of course, well, the number of ways to do that here is Sn minus 2. And the number of ways here is Sn minus 2. And I can combine them. So it's going to be S squared of n minus 2. So therefore, in this setup, there are S squared of n minus 2 ways, or Sn minus 2 all squared ways of doing this, because it's just the number of ways to do this one times the number of ways to do this one, which is this times this. Now, what if you put a 1 in the middle? Well, if you put a 1 in the middle, or in the n minus 1th term, I should say, then there has to be 2 zeros either side, which means here you only have n minus 3 terms left, and here you also only have n minus 3 terms left, which means, again, I just need valid sequences here because I can have any number next to this 0 and any number next to this 0. So that's going to be Sn minus 3 and Sn minus 3. And again, you times them together to find the total number of ways you can construct this, which is Sn minus 3 all squared. And therefore, the number of ways to build S2n minus 3 is Sn minus 2 all squared plus Sn minus 3 all squared. And by the conclusion we had in the previous part, that the s's are related to the f's via this, and therefore this here, we can just convert that to be this rule here, which is what they wanted us to get. The next part is part 6, show a very similar thing here. So we're going to do basically the same thing that we did with this thing here. Firstly, let's convert this to an S formula to show. So let's do the same things. S is always 2 behind the f's, and we'll say this is the thing that I want to show. So I need to consider sequences of length 2n minus 2 this time. Let's consider still the n minus 1th position or term, and think carefully about how many are either side now. There's clearly n minus 2 on this side, because of course it's just 1 less than the n minus 1th, which we've got to. And then, okay, so what do we need over here? How many are going to be left over here to make this many in total? Well, I think it's n minus 1, because if I add those together, I'll get 2n minus 3, and then including this middle term makes 2n minus 2. So, okay, well, there's Sn minus 2 ways of doing this and Sn minus 1 ways of doing that. So multiply them together to find how many ways there are of doing this setup, and then also consider the 1 in the middle. So that's the total number of ways of doing this setup. With the 1 in the middle, we need 2 zeros either side. So there are only going to be n minus 3 terms left over here and n minus 2 terms left over there, times the combinations to do those things together, and you get this. And now, therefore, we have Sn 2n minus 2 equals this plus this, because those are the two things we have to add to make all of the different combinations here. So we have this plus this, and now that kind of looks like this here, except I've got an Sn minus 1 term that I don't want. So now I go all the way back up to here and say, well, okay, Sn minus 1 is Sn minus 2 plus Sn minus 3, based on the Fibonacci idea that we know the s's follow. Now we can expand out, and we end up getting exactly what they wanted us to get, I think, which then relates back to this thing here. Unfortunately, I have no idea how to do part 7. I guess I only got 98 on this paper, which is a shame. I've got some various ideas, all of which don't seem to go in the way that I want them to, so we're just going to skip it. Apologies for that. Someone in the comments will tell us how to do it, I'm sure. So anyway, moving on to question 6, which is for the computer scientists, which I'm not particularly interested in, but for completion, I guess we'll just go ahead and do it. We've got this kind of idea where leafs are called these things at the end, so 4, 7, 2, and 6 in this case, and 3, 4, and 7. You're using all the digits 1 to 8, and you're just finding ways to draw them in various different ways. So you can have as many branches coming out of a, what are these called? A parent. You can have as many branches coming out of parent as you want. And to make the code, you delete the smallest leaf. So in this case, you delete 2 and write down its parent, which gives you an 8. And then once the 2 is deleted, the smallest leaf is a 4, so you delete that and write down its parent, which is a 5. And once the 4 is deleted, the smallest leaf left over is a 6, I believe. Is that right? Yeah, it looks like it. So then you delete that and write down the smallest leaf then would be a 5, of course. So you delete that, write down a 3, and then you delete the 6, write down an 8. And then you delete the 7, write down the 1. Then 1 becomes the smallest leaf, delete that, write down an 8. And then delete the 8, write down the 3. There's a few things that we can gain from doing that. Firstly, we can just do it with T2, I guess. So smallest leaf is 2, so delete it, write down 6. Then the smallest leaf is 3, delete it, write down 1. Then the smallest leaf becomes this 1 after this has been deleted. You write down 6 again. Then the smallest one is 4, delete it, write down 5. Then 5, write 8. Then 7, write 8. And then 8, write 6. And this will be the code. There's a few things we can learn from this. Firstly, the code is going to be 7 digits long, always. So that's one thing to say. The second thing we can learn is that we never write down the leaves, right? Like, notice how this code didn't involve 4, 7, 2, 6. and this one didn't involve 3, 2, 4, or 7, we only ever write down parents. So if we're seeing a code like this means that 8 is a parent. It's not a leaf. But how do we write a code in which just all exists 8? Well, that's just if 8 was a parent to all of them, and we just deleted 1, wrote 8, deleted 2, wrote 8, deleted 3, wrote 8, and so on. And likewise for this one, notice how this has all the numbers except for 8. So therefore, 8 is the only leaf because we've never written it down. Except it can't be the only leaf, right? So how do we go about doing this? Well, notice how we've written down all of the other numbers. So all the other numbers are parents. And the only way to make that work is to draw a tree that looks a bit like this, where 8 is the first leaf, which means we never write it down, but we write down every other one because it's a parent going on the line all the way to there. Like I said, leaves we don't write down. So the leaves of this are 2, 4, 5, and 7, the numbers that are missing. The digits in this code that have 1 as their parent, well, clearly the first thing that got deleted had 1 as its parent. And the first thing that gets deleted is the smallest thing, so that must be a 2. Then something else got deleted in order to write down a 6, so that must have been 4. Then 5 got deleted and you wrote down a 1, so therefore 5 is also a child of 1. And I think that will be the answer to this. I think it will just be 2 and 5, and then 7 I think must be a child of 8 because of these two 8s next to each other. Anyway, then I started drawing it. I think I started drawing it first just to make sure I was right. So okay, 8 is definitely the source. Because it's the one here. It has at least 2 children because 2 8s, actually 3 of them appear here, so it must have 3 of them. So like I said, I think 7 is down here, but I know 3 is. So I wrote that down first. But 3 is a parent of something because it appears earlier in there. I know 1 is also must be a child of 8, I guess, because both 1 and 3, they must be parents because otherwise they'd be deleted before some of these numbers. And therefore they must also go up to 8 because 8 is the last thing left over. So that was how I kind of got this idea. Keep going with this 6. 3 goes down to a 6. 1 must be a 2. Like I said, 2 is the first one that gets deleted, write down a 1. Then something gets deleted and you write down a 6. A 6 must be a parent of 4. Then something got deleted, wrote down a 1. So that must be the 5. And then the only thing that's missing is the 7, which gets written down in between these two 8s. And we have this here. So okay, yeah, and therefore 2 and 5, like I said before, were the only children of 1. Briefly describe the procedure. So firstly, you identify the missing values. Those are the leaves. Once they're in order, once you've ordered the leaves, you could just say that those are the parents. You could write down the parents because those are, why have I said it? Once they're in numerical order, you could say, okay, well, 2 is a child of 1, 4 is a child of 6, 5 is a child of 1, and 7 is a child of 8, somewhere in here. You can't put it down there because otherwise 3 would have been deleted first, so 7 must appear here. Otherwise it would be deleted. Otherwise the 3 wouldn't have been deleted earlier, which it must have been. So you can kind of draw it from that thing. I'm being quite vague here because I'm not entirely sure how you're supposed to word any of that, but that's kind of the system. You work from the top downwards, having ordered the leaves and inputting them in the middles where they must have been deleted. I don't really know how better to word that, so I'm just going to say that's probably okay, but I don't know whether that would have gained 2 marks. Anyway, the last part is the number of trees greater or smaller than this. So the number of distinct trees must be equivalent to the number of distinct codes. So for every tree, there must be a corresponding code and vice versa. So therefore, we don't really want to count up the ways of drawing trees. We can just count up the ways of writing codes. Now you have 8 choices for each of these digits, and there are, of course, 7 digits. So that's 8 to the 7 number of codes. Therefore, the number of trees is also 8 to the 7. 8 is 2 cubed, which makes this 2 cubed to the 7, which is 2 to the 21, which is 2 to the 10 times 2 to the 10 times 2, breaking up this 21. 2 to the 1 here adds up to make 21. This is 1,000, this is 1,000. Well, actually, it's more than 1,000, and this is more than 1,000, and this is 2. So this is slightly bigger than 1,000 times 1,000 times 2, which means, therefore, that this is slightly bigger than 2 million, and therefore there are more than 2 million codes, I think is my final answer. I think that's the whole paper done. Apologies for not quite getting all of that, but there are no mark schemes out, so there's not really much I can do about that for now. I hope someone can come up with some answers in the comments, or we'll just wait for the mark scheme to drop and we'll know what we were supposed to have done.